All right, let's dive in. Today, we're going to tackle one of the most fascinating and, let's be honest, mind-bending topics in all of science, the incredibly strange world of quantum physics.
And we're going to zero in on one key player, the photon, that fundamental little particle of light. Specifically, we're talking about its energy and its momentum, because understanding those two things cracks open a puzzle that classical physics just couldn't solve.
So let's start with that puzzle. It's a real head-scratcher, a question that for a long time just didn't have a good answer, and it really sets the stage for everything we're about to get into.
So get this, we know for a fact that light has zero mass. So how in the world can sunlight physically push the tail of a comet away from the sun? Think about it. In the world we're used to, something with no mass can't push anything. It's like trying to get knocked over by a ghost. It just doesn't make sense. To figure this out, we need a whole new way of looking at light.
And that new way of looking at things introduces us to the hero of our story, the particle that solves this whole mystery, the photon.
So a photon isn't just some vague part of a light wave. No, it's a fundamental packet of energy, a single, discrete chunk of light. It's the absolute smallest amount of light energy you can possibly have. You can't get any smaller.
And here's where things get really, really weird. A photon has zero mass. It travels at the fastest speed anything can travel. And this is the crucial part, the key that unlocks the puzzle. Even though it has no mass, it carries both energy and momentum. It's that momentum that gives light its ability to push.
And look, this isn't just some wacky theory. This idea is a cornerstone of modern physics. Understanding the photon is absolutely essential for describing how light and matter interact at the tiniest scales imaginable.
Now, this idea of light coming in packets, or chunks, brings us to another huge, mind-bending concept from the quantum world. The idea that energy itself is quantized.
So, what on earth does quantized even mean? Well, think about a ramp versus a staircase. On a ramp, you can be at any possible height, right? It's continuous. But on a staircase, you can only be on step 1, or step 2, or step 3. You can't stand on step 1.5. Quantum energy is exactly like that staircase. You can have the energy of 1 photon or 2 photons, but you can never ever have the energy of 1.5 photons.
And you know what? We have fantastic proof of this. When you look at the light that's given off by an excited atom, you don't see a smooth, continuous rainbow. Not at all. You see these very sharp, distinct lines of specific colors. Each one of those lines is the fingerprint of an electron jumping between 2 specific steps on that energy ladder, spitting out a single photon with a very precise, quantized amount of energy.
Okay, so we've got the concepts down. Photons have energy, they have momentum, and it all comes in packets. Now, let's get practical and see how we actually calculate these incredibly tiny but powerful values.
To really see how this works, we're just going to walk through a classic example. This will show you exactly how the formulas work in a real situation.
So, first step. Say you know the wavelength of some light, in this case, 550 nanometers. How do you find the energy of a single photon in that light? Well, you use this formula right here. You just plug in Planck's constant, h, and the speed of light, c, then divide by the wavelength. That gives you the energy.
Now that answer in joules is a crazy small number, right? All those zeros make it really awkward to work with. So physicists often convert it to a much more manageable unit called the electron volt, or EV. In this case, our tiny number becomes a nice clean 2.3 EV.
And finally, let's get the momentum. This part is surprisingly easy. You just take the energy that we already found, the one in joules, and you divide it by the speed of light, and that's it. Just like that, you've calculated the momentum for a single massless photon. Pretty amazing? Okay, you've seen it done, now it's your turn. Time for a quick fire round to make sure all this is sinking in. First question, let's run that last problem in reverse. If I tell you a photon has an energy of 4.3 eV, can you figure out its wavelength? So the first thing you have to do is convert those electron volts back into joules. Then you take our main energy formula and just rearrange it to solve for the wavelength. Plug in the constants and you get 289 nanometers. Okay, next part. What's the momentum of that very same photon?
You got this. It's that beautifully simple formula again. Momentum is just energy divided by the speed of light. Take the energy in joules, do the division, and you've got your answer.
All right, final challenge. This time, I'm not giving you wavelength or energy. I'm telling you the frequency. What's the photon's energy now?
For this one, there's an even simpler formula. Energy equals Planck's constant times the frequency. E equals hf. You just multiply those two numbers together, and that's it. It gives you the energy directly in joules. Fantastic. So after all that, what are the big ideas you absolutely have to walk away with? First, light is fundamentally weird. It acts like both a wave and a particle. Second, energy isn't smooth. It comes in these discrete packets. It's quantized. And third, the solution to our comet tail mystery, a massless photon still has momentum, and that momentum is directly linked to its energy.
Which leaves us with one last big thought. We've been talking about the tiny, tiny push from a single photon. But what happens when you concentrate trillions upon trillions of them into a focused beam, like a laser? All of a sudden, that tiny quantum push becomes a real measurable force. This is the science behind incredible ideas like solar sails that could push spacecraft to other stars powered only by light. It just goes to show you, a single tiny quantum idea, when you scale it up, could literally move worlds.